workshop focused on energy storage solutions for net zero. And you will have now the pop-up probably saying that this meeting is recorded. So I just say that I hope you are all okay, and the speakers have been okay as well with that. So before I start, maybe Angela, you could share the slide to introduce who we are and what we are kind of doing a little bit and what our aim is. And so we are the Early Career Research Committee of the SuperGen Network for Energy Storage, and consisting of, as you can see, Jianing, Hui, Ola, Amruta, Binyan, and myself. And the ECR lead of the network will actually give the first talk, as you see in the program. Next slide, and Angela, please. So he will give the first talk. It's Yongyang Li from the University of Birmingham. He's currently reader there, and he will introduce the network, introduce a bit more around the global scheme of things in the SuperGen. And this workshop is more aimed to really get you as early career researchers engaged in storage solution for net zero, and also see your view, see your perspective in the workshop afterwards. So we have the first session starting on energy solutions towards net zero. So having a little bit of a more large scale overview of solutions. And then the session 2, after a short coffee break, will be on materials for energy storage, where we have excellent talks as well around how to design really the atomic scale of things towards net zero. And in the workshop, then it's really up to you, up to everyone, the speakers, the participants, to engage in small breakout rooms. And we have prepared a list of questions that we'll share closer to the workshop that you could then hopefully use to have engaging discussions, which we then will summarize in a 10-minute concluding session and summary. And yeah, I think without further delay, I would like to hand over to Yongyang, who will introduce the network first and then give his keynote talk.
Yeah, thanks very much, Mila, for your introduction. Can you hear me, everybody? Just yeah, good. Thank you. Yes. Thank you very much. I apologize. I got a cough these days. Yeah, so it's my privilege to give this keynote talk. I give a title on energy storage in the path of net zero, essential, desirable, or optional. Actually, because this is an ECR form, so instead of introduce my own research, I prefer to share some of my opinion on the energy storage research. Hopefully, this can be be helpful for your career development, including, for example, prepare a research proposal or things like that, or research paper. Okay, firstly, that this event was sponsored by SuperGen Energy Storage Network Plus. So I'm gonna give a very brief introduction about the Network Plus. So at a glance, this Network Plus is chaired by Professor Yulong Din from the University of Birmingham. And we have 19 academics from 12 institutions for this network, with 1.2 million pound funding from EPSRC. And among this fund, this 1.2 million, we have allocated 450K for flexible funding. So basically, this network itself is going to use to support mainly their efforts to the early career, career development of young researchers. And apart from that, we have a 100K from the International Energy Storage Alliance for joint international projects. And we also have about 2 million pounds in kind support from 34 project partners. The project itself is 48 months in duration, and it starts from September 2019. So this network covers all the energy storage technologies, including electrochemical, electrical, thermal, mechanical, and chemical. And more importantly, we cover not only the technology itself, but also the integration of the energy storage in any energy networks, and as well as the related, for example, energy economics, policy, and environmental impact, yeah, all the related area of energy storage, including AI and big data. So our vision of this network is to connect and serve stakeholders across the whole energy community, advancing and champion UK energy storage research and deployment. Yeah, as mentioned, so one of the work package of this network is about early career researchers, and I and Paul from the UCL acted the co-lead for this work package. So the activities so far for the ECR is yeah, we dedicated fundings to support research activities, and also the networking opportunity through dedicated events, and we support ECR regarding the development and the flexible fund proposals, and also yeah, create a ECR committee. And also we connected with contact with other superchain hubs for the further development of ECR career, including webinar series. And one thing I want to mention is this Net Zero conference was going to held on between 1st and 3rd of September this year. This event is jointly organized by the 6 superchain hub. So yeah, I encourage you to try your best to attend, and this should be a very fruitful event. Okay, come back to my talk today. As I mentioned, instead of discussing specific technologies, I would like to share some of my opinions about energy storage based on my experience about the 15 years working in this area. Yeah, let's start with the first very simple question: what is energy storage? So basically, when we're working on energy storage technology, we mean the narrow definition, which is the conversion of energy by using devices into various forms that can store for later use. So in this definition, you can find that energy storage is different from good storage. So for other storage only element, that's one storage, right? For energy storage, most importantly, that is the conversion, because energy cannot exist without a carrier. So we know that in the conversion process, energy may lose, and this is called the efficiency of energy storage processes. And this is so how to have a deep understanding of the energy conversion process is quite important to understand the role of energy storage. We know that energy storage, actually there are 2 elements. One is energy, one is storage. Energy is the power times time, right? This is what energy. And as I mentioned, energy cannot exist independently. It needs an energy carrier. So it can exist in different forms, and based on the form of energy storage, we have actually different energy storage technologies. At the moment, we can store energy in the form of mechanical, chemical, electrical, and thermal, and very hard to store energy in the form of nuclear, light, or sound. And yeah, probably with your effort in next couple of years, next couple of decades, if you can also store energy in these 3 forms, in particularly, if you can store energy in the form of nuclear power, then the density of energy can improve dramatically. Okay, not sure if it's a dream and need your effort. Yeah, we already know there are different kind of energy storage technologies. So between different energy storage technology, I want to emphasize that the 4 different energy storage technologies that mainly did 2 different functions. One function is for energy. Basically, it's for larger scale. More importantly, it's for longer duration. And the other is for a short duration. It's mainly for power function. Okay. Based on this, actually, personally, I prefer call this technology more to power storage technology. We'll call this energy storage technology. There are 2 different features between these 2. And in most cases, for the energy storage technology here, the technology itself can be fully decoupled. That means the charging discharging process can be decoupled with energy carrier itself. Well, for this power function technology, it's fully integrated. Okay, so for a specific application, there are 2 kind of costs for energy storage. One is based on the amount of energy, the other is based on the power rate. So these two are equally important, depends on the specific application. And this is quite important to determine that if a specific technology is suitable for a specific application. So while we discuss energy storage, bear in mind that actually fossil fuel is the most important form of energy storage, right? And fossil fuel actually at the moment is one of the main competitor of energy storage. And in the future, probably other fuels, for example, methanol or ammonia, could also be the competitor of energy storage. Yeah, this is the broad definition of energy storage. Yeah, let's think about another simple question: why energy storage is needed? So if we think about the supply chain of other goods, right? Traditionally, we have a lot of storage capacity, but nowadays with the technology improvement, we prefer more zero storage capacity, right? Prefer more this just in time manufacturing process, because storage itself going to cause loss, going to waste. So this actually is a very important question for energy storage, is that when you develop an idea, because energy storage is kind of service, not a product. So for specific application, the first question you ask is that possible to avoid energy storage? If possible, yeah, that is also another solution. Only in the case that without any storage, it's not functional or it is not efficient, then we need any storage in the whole chain. The reason that for energy we need energy storage is that a big change or switch from the fossil fuel generation to renewable generation. So for fossil fuel generation, the electricity mainly is generated by the just-in-time principle, right? While for renewable generation, you cannot control the generation, you cannot control the availability of renewable sources. That's why that we need energy storage to balance the generation and the demand. And this is true. One example I give here is that in Scotland last year, wind farm was paid about 3 million per day to switch off the turbines. In other words, if we can develop effective and cost-effective and cheap energy storage technology, the energy itself, charging process, energy is free. Meanwhile, we may get paid for consuming this energy for later use. Okay, in other words, the real application depends on a specific scenario. Okay, I also would like to discuss that what are the main requirements for energy storage technology. Here I can list 2 or 3. And the first one is the most important one we always call round trip efficiency. So for all energy storage process, basically we have 3 processes: charge process, energy in, and storage process, leave energy carrier there, and then discharge process. We regenerate energy for specific use. And the round trip efficiency is the ratio between the energy output to energy input. Apparently, round trip efficiency or efficiency is quite important for a lot of application. And also, of course, for real application, there are other factors. For example, the cost and the lifetime. Yeah, in a lot of research, and we emphasize that the round trip efficiency is important, but that is, in my opinion, round trip efficiency is not the only rule, to determine if the technology is suitable for real application. Here, I prefer to give one example. This is power to fuel. More accurately here, this example is power to methanol, right? So in this process, think about the round trip efficiency. We have renewable electricity. Firstly, we produce hydrogen, and then use the hydrogen combined with CO2 and to generate. Here is methanol. We can use the same approach to generate ammonia. So you can see that in this process, actually the efficiency is quite low. From here to here, my estimation efficiency, yeah, about 20–30% only, because there's a lot of irreversibility in this process. And meanwhile, while we reuse, let's say, the methanol or ammonia to regenerate electricity, right? The efficiency is about 40%. So the overall, the wheel-to-wheel efficiency is only, yeah, probably 10–20%, which is very low compared to other technologies, for example, battery, right? But in the real net, zero future, the ammonia or the methanol is also another very important way to store energy. Even the round trip efficiency low, but it has a lot of other advantages, which other any storage technology, for example, battery cannot achieve. For example, very long duration storage, right? Which is impossible for batteries, right? This is one example. So I would like to say that any storage is a service rather than a product. It only makes sense to evaluate the performance in specific application scenario. Another important parameter for any storage performance is the cost effectiveness. As I mentioned, so any storage consists of at least 3 processes, right? Charge, discharge, and storage. So compared to other power generation process, apparently the cost is very high. And any storage is a service. So generally the annual utilization hours is much smaller than other power generation facility. For example, for nuclear, probably annual hours 8,000 hours. For any storage, probably only 100 couple hours, right? Much less. And this is going to increase the cost apparently for the unit energy generated. In other words, any storage cannot be considered as a generation. However, in most cases, at least at present, the flexible generation is a competitive for energy storage. Okay, I already mentioned this, so depends on different functions. Some of the storage technology provide a function of power, the other provide a function of energy. And the main different feature between this is a fully coupled technology. While in this case, the energy carrier can be fully decoupled from the charging discharging process. This is important for the selection of specific technology for specific application. And there are a couple of ways to improve the cost effectiveness of specific energy storage technology. So here I give some example. The first example is the multifunction solution. For example, in this case, in the the smart grid or things like that, right? EV in the future, I believe, gonna play a very important role. So actually, EV have batteries. The main purpose of EV actually, not purely energy storage, because we need power, we need fuel to only for mobile application, right? But with development of a smart grid, so if when we do not drive, when we park the vehicle, we connect to the smart meter. So this EV can smartly determine to charge from the grid or produce electricity to the grid. And in this case, when we park the vehicle in the future, probably, and each vehicle is a single energy storage station. It is, in other words, the vehicle is a vehicle, but it can have the function of energy storage. So in this case, because it's a multifunctional facility, we can decrease the capital cost or increase the cost effectiveness. And this can be realistic or be utilized in real application very shortly with a lot of smart tariffing. And here I give one example. Here you get paid if you export the electricity to the grid, right? This make sell the grid from the EV to the grid is possible. Another way to improve the effectiveness of thermal and of energy storage technology is the decoupling of energy conversion process. For example, for the CSP process, right? Anyway, even without the storage, we're gonna collect the solar radiation, we're gonna convert it into heat, use this heat to drive the steam turbine process, right? So here in this case, we only add 2 tanks to decouple the thermal heat generation process and the thermal utilization process. We add additional function of energy storage for the system, right? And this can decrease the cost of the storage itself. And actually, compressed air and storage is another example. Actually, compressed air decouples the compression process and power generation process of conventional, gas turbine technology, right? Another way is storage integrated energy generation. For example, solar collector for hot water, right? Anyway, you're gonna produce hot water in the solar collection process, and just by store, small amount of hot water, and the function of storage for this process. And for cold storage, just the same. Anyway, the refrigeration process gonna produce cold water. So if we add a cold water storage volume, we're gonna, add the additional function for this unit for energy storage, not, produce a new device or equipment only for storage. My personal estimation of future energy storage installation is that, for short term, the centralized big scale gonna play a leading role. While for long term, the demand side multifunction and storage will, play a leading role. Lastly, I would like to compare electric and thermal. So in our energy triangle, there are three elements: that is electricity, fuel, and heat. And the fact is that the demand of electricity actually is more or less more stable, more smooth, because the demand depends on a lot of factors. While the demand of heat and cooling, consistently depend on, for example, the weather, the ambient temperature. In other words, the heating and cooling might be much more challenging than electricity itself for future, energy scenario. Okay, that's only I wanted to talk today. Thank you very much.
Thank you, Yongliang. That was a wonderful talk, and I think also the introduction of the SuperGen was very helpful for our participants. And I also would like to mention here that if you want to get involved, please contact Angela. I think her email was always at the on the Eventbrite website, but we can also share that with you later. So we do want to have the ECR committee be growing in the future. So yeah, contact us if you want to be part of it. With this, I think I hand over to Bianjan to chair. Is he?
Thank you, Lumina.
Yeah.
Thank you. Morning, everyone. Welcome to this session, session 1. So my name is Bianjan from University of Birmingham. I'm currently a research fellow working on thermal energy storage. So in this session, we have 3 speakers. And each speaker is expected to give 15 minutes presentation, and also you can ask questions. All the questions are welcome. So you can type your questions through the chat function just at the bottom of the screen, and we'll try to let the speaker to answer as many questions as possible. But as you know, the time is limited. But fortunately, we have a I think we have a discussion after the 2 sessions. So during the discussion, you can also ask questions and share your ideas with other ECR members. So firstly, I'm honored to introduce our first speaker, Andreas Olympius. Firstly, allow me to introduce a bit about Andreas. So Andreas is currently a 3rd-year PhD student at Imperial College London. So his main interest is the design and operational optimization of heat pumping technologies, as well as identification of energy system implications of electrification and the larger scale electricity storage. So Andreas, are you ready? I'll leave the screen to you now.
Hello, hi. Yes, thank you very much. It's a very interesting workshop, and thank you very much for the opportunity to present. Can you see my screen in presentation mode?
Yes.
Yep. Okay, so yes, thanks a lot. As you said, 3rd-year PhD.
Andrea,
Yes.
sorry, I don't think it's exactly presentation mode. You cannot see the whole slide properly.
Really?
If you click display settings and switch the screen, and that will be fine. Yep, swap.
So, oh, okay. Is that better?
It's at different resolution, I think. Maybe do you want to stop the sharing and reshare?
Yeah, let's try this. Let's try this. So let's share this again. Okay. Yeah, now it's full screen. Is that still?
No, but we still actually have time. So maybe if people have questions to Yongliang, please go ahead and ask while Andreas is maybe setting up, not be too stressed.
How about this?
Perfect now.
Yeah, that's good.
Thank you.
Oh, okay. So yeah, I guess I can go, except if somebody wants to ask anything.
Yeah.
Okay. So yes, hi. I'm as you said, a third year PhD student in the Clean Energy Processes Laboratory in the Department of Chemical Engineering at Imperial College. Christos Markidis is the leader of the laboratory, and thanks a lot for the opportunity to present on our work on the progress and prospects of thermomechanical energy storage. So, of course, in 10-15 minutes, we can't go in much detail, but what I want to say is that we conducted this large review with a lot of other people. We basically collaborated with a lot of well-known experts in the field of long duration, large-scale energy storage. And with their expertise, we managed to review a lot of these main large-scale options and then analyze them and compare them thermodynamically and economically as well. So this paper has been published in a relatively new journal called Progress in Energy. So all the talk today is about this review. So how does this research address the discussion topics of the workshop? Of course, as we know, major economies, including the UK, are aiming to achieve net zero carbon emissions by 2050. And there have been some significant advancements in renewable generation, like wind and solar. For example, renewables have taken 47% of the total electricity generated per fuel in the first quarter of 2020, which was a record. And these renewable systems seem to be gaining increasing momentum. But as we of course know, they are not always there. Wind does not always blow. And since these technologies are not always able to provide the electricity we need solutions that can ensure that we have a system that is stable and reliable. And especially in the very near future, when large sections of hidden transport are probably going to be electrified, we're going to face significant increase in energy consumption, energy demand, and therefore we need storage. Storage is designated as an imperative piece, basically, to any energy transition pathway towards decarbonization. So in terms of possible options, there are a lot of large-scale, long duration options. The main option is pumped hydro energy storage, which is the most widely used technology. I think it's 96% of the total world capacity or something like this. Of course, there are some problems with this option, mainly because it's geographically constrained. You need certain geological features. There are also certain environmental concerns people talk about. And main competitors to this technology are batteries, of course, especially lithium-ion batteries are gaining momentum. But of course, lithium-ion batteries become less suitable as we move to very long duration and very long lifetime applications. Basically, their costs seem to be relatively high when we move to very large scales, at least for now. Flow batteries also seem to be another option, similarly to lithium-ion batteries, though they still face high costs at very large scales. So this is where thermomechanical energy storage jumps in. And this type of storage refers to the process of storing energy based on transformations between mechanical and thermal energy. Although these systems are at a relatively early stage of development, they have recently shown to have competitive technical and economic characteristics when compared to these other main options. For example, in this figure, what we can see is a lot of different storage options for large scales as function of discharge power rating on the left and discharge energy capacity on the bottom. And what basically we can see from this figure is that usually batteries appear on the bottom left, so relatively low power ratings, relatively low energy capacities. And as we move to very long durations and large ratings, we get a lot of thermomechanical energy storage options becoming candidates. And there are three main types of thermomechanical energy storage. These are compressed air energy storage, liquid air energy storage, and pumped thermal electricity storage. So these three main types of thermomechanical energy storage are at a different level of maturity, but they are all experiencing significant growth. Compressed air energy storage, for example, is a commercially applied technology since the 1970s. There is the Hundorf plant in Germany, a 321 megawatt system. There is also a 110 megawatt one in Alabama in the US. So this is an applied technology. It's based basically on using power to store, to compress air, store it, then you can expand it through some turbine to get the electricity back when you need it. And storage of this technology depends on having some available underground caverns. If those are not available, people have looked in other possible solutions like overground high pressure tanks or some novel underground balloons, underwater balloons that basically can avoid the dependence on geological formation. There are significant advancements in this technology, some advanced concepts that also can store heat as well as compressed air, so increasing the efficiencies. In terms of liquid air energy storage, this is also an interesting concept. It's based on just using power to liquefy air, and when you need the electricity back, you can just evaporate the air, expand it, you get the electricity back when you need it. And there is a 350 kilowatt pilot plant at the University of Birmingham. There is also a grid scale demonstrator. I think it's 5 megawatt in Greater Manchester. So it's gaining some momentum, and there are also some other even larger facilities at the moment that are under construction. And lastly, the last of the three is pumped thermal energy storage. This is based mainly on storing electricity as a temperature difference between some reservoirs, either solid or liquid. And there is a 2 megawatt system demonstrator already in place. There are also some other commercial interests from other companies. So it's also evolving. And when we look at the different industrial applications and also into the different academic research, we can see that most of these thermomechanical energy storage options, yes, they target ratings that are often higher than 10 megawatt, and they also target durations that can be often longer than 1 day. And at this scale, other technologies have difficulties in competing. Of course, one of the main characteristics that we have to look at, as also Yang mentioned, is round trip efficiency. And thermomechanical energy systems have shown to have round trip efficiencies close to 60%. Compressed air has shown significant advancements, maybe 10-20% in the last years, due to the ability to store heat as well as compressed air. Also, liquid air energy storage has, we would see efficiencies close to 40 or 50% in the past, but the recent research shows efficiencies even higher than 60%. Similarly, pumped thermal electricity storage usually estimates at about 60 to 65%. And all these estimates are relatively lower than pumped hydro or batteries. So there is some gap, because pumped hydro or batteries, of course, depending on the type, can have efficiencies usually above 70, even sometimes close to 90%. So there is some gap between thermomechanical energy storage options and these options. But the gap has been reduced in all these years, and there are prospects that the gaps can be reduced further. Also, of course, round trip efficiency is important, but most important characteristic is the capital cost. And when we look at the predicted capital costs of these systems, we can see that they are actually quite competitive compared to batteries. Maybe not compared to pumped hydro. Pumped hydro is always the cheapest option if that's an available option. But when we compare these technologies to batteries for large scales, we can see that they have sometimes even lower costs. So they can definitely be competitive. And I'm not going to go in detail here. I just want to mention that in our review, we also developed some thermodynamic models and economic models of these options. And we can therefore make predictions for the costs of these systems for any different power rating or discharge duration. So we can basically compare the different options at a different scale at each time. So it's a very useful comparison for us. And yes, I'm not going to go in detail here, but I just want to mention that, for example, we could compare the energy capital costs of technologies for different power ratings, like we see on these two figures here. We compare technologies on a power rating of 1 megawatt and a power rating of 300 megawatt. And if we could make some main conclusions, those would be that, okay, compressed air is the cheapest option whenever we have an available underground cavern. If we don't have one and we go to high pressure tanks, then it becomes one of the most expensive options when compared to other thermomechanical energy storage options. Also, liquid air energy storage appears to be slightly expensive at low power ratings, but it's becoming very much more competitive in high when we go to high power ratings. And lastly, pumped thermal energy storage is shown to be very competitive at high power ratings, especially when we look at packed bed thermal stores. So I'm almost done. I'm just going to conclude here to say that thermomechanical energy storage options also have some other advantages. For example, you can link them to waste heat sources. If there's some waste heat available from any other plant, you can use it. And apart from that, if there is also some demand for heat, these systems can, during discharging, also provide some heat. So if there is demand for heat, there may be reductions in the efficiency that is required for the systems, therefore making them more competitive. And their future perspectives, of course, depend on increasing the round-trip efficiency and reducing the system cost, which in turn depends on us developing higher performance and lower cost components. Further testing is required to develop these components, and also we need some smart control systems that can improve the competitiveness of the systems in large grids. So that's all. Thank you very much for your time. I hope that was interesting. Yes, let me know if there are any questions. Otherwise, yes, thanks very much for the opportunity.
Thank you. Thank you very much, Andres. It's a very good talk to compare different kind of thermochemical, thermomechanical energy storage method. So can remind the audience, if you have any question, you can ask Andreas now, and also you can type your question using the chat function just at the bottom of the screen. So I think there's a question from Quarantine, Andreas. You can see from the screen. So saying are there any hazards in storing air under high pressure? I think that's a good question.
Yeah, I mean, it's of course it's not an easy question. I mean, it's always a problem when you go to high pressures. You need more, you need better materials, larger thickness of materials. So I don't think that if you do it, it's that dangerous, as long as you invest enough money to make it safe enough. So I guess it just makes the system more expensive if you go to those options. Of course, I'm not an expert in compressed air, so I guess other people may have much better understanding. But that's my view, I think. Yeah.
And there will be two more questions. So first one, is there any chest experimental setup, Andreas?
Yeah, so chest is a kind of pumped thermal energy storage. I think there is one. I don't remember fully, but I'm pretty sure there is one. They are developing one because chest is based on already existing components. It's based on steam cycle. It's very easy. So it's I think it's actually happening at the moment. I'm not exactly sure, so sorry about that, but I think there is an experimental setup in place. And there is one more.
Yeah, I think it's about modeling. It's about the counter clause?
Yes, so the relationships, okay, of course, once you're changing the size of different technologies, your costs changes, and also sometimes your component have to change. For example, in pump thermal, you cannot have super large reversible piston machines. So yes, these relationships are relatively complex. We tried within this work to make some consistent assumptions for all technologies so that we try to be as fair as possible in the comparison. But yes, the main reason for the cost changing as you go for different discharge durations for different power ratings is because you know, there are economies of scale. As you move to larger components, their specific costs go down. So of course, the specific cost of the technology goes down. So I hope that answers that question.
Okay, thank you, Andres. So thank you for your questions, everyone. So if you still want to discuss Andres, maybe you can discuss with him after the session. We'll have a breakup rooms, and you can share your ideas about the thermal mechanical energy storage ideas with Andres there. Okay, so now I think it's time for our second speaker. So our second speaker will be Dr. Wei He from University of Warwick. Dr. Wei He is currently a Royal Academy of Engineering for Development Research Fellow in the School of Engineering, University of Warwick. And his research interests include energy storage, low carbon heating and cooling, and also sustainable separation technologies. So Dr. Wei He, I leave the screen to you now.
Yeah. For the kind of introduction, can you hear me properly?
Yes, I can.
And also, can you see my presentation in the full screen? Okay, yeah. So thanks for the kind introduction. So today I'll talk about the large-scale electrical energy storage towards a net zero energy future. Yeah. So I think previous two speakers gave a very good presentation, about energy storage, particularly in the large-scale electrical energy storage. So today, I'll try to, touch three points. The first one, like the why energy decarbonization needs large-scale electrical energy storage. So, everyone knows climate change. So this kind of definition of climate change, from Wikipedia. So in general, it's both global warming due to the emission of greenhouse gases and also the resulting large-scale shift in weather pattern. So in order to mitigate climate change, we need to mitigate emission of greenhouse gases. So if we look at, where this emission come from, so majority of them actually related to energy. So either energy generation or end uses, or something like mining or other uses of fossil fuels. So we need to, energy decarbonization, which kind of get rid of fossil fuel, actually is very critical to securing a global transition to net zero. So yeah, so UK actually, achieve, very good achievement in the last several decades, by reducing its emission to a very level, actually, close to since like 1888. But if you look detail about, how UK achieved this kind of the, carbon emission, so majority, like 3/5 of the emission actually, reduced by, phasing out from like coal-based generators. So, as we know, like coal almost there can no generation or almost very low generation at the moment. So what are the next step, for significant power decarbonization? So now if we look at briefly, have a very quick simple example to show like how the electricity system works in the UK or in other system as well. So basically we have very low demand, kind of we want to meet. And currently we have some low carbon sources like nuclear, like solar, wind, and some biomass. So there is critical portion of generation from dispatchable generation. And in the UK, most of them actually gas power generators. So this generator, always try to, meet the mismatch between the intermittent or like low carbon supply, and also to meet the variable demand. So people may ask, like, if we want decarbonized system, we can simply, keep installing renewable energy like solar and wind and replace the fossil fuel. So can we really do that? So here is kind of simple example. So it's basically an electricity system like what we may have at the moment. We have like a relatively low penetration of renewable energy, something around 20–30%. And so actually the generation capacity required, for the dispatchable generation is kind of worst case between the kind of, when the wind is not stopped blowing, and we need this generation to secure 100% reliability. And although we can simply increase that penetration like of solar and wind, but the problem is like that worst case won't change much, because like if there are no wind, no matter how much wind turbine you install, there are just no wind jet power at all, or almost close to zero. So at least, if we need to really achieve a very high reliability or close to 100% reliability system, probably a similar gas power generation capacity, we still need to be there. And we also, from a low carbon sources, and also that sources should be dispatchable. So the question becomes, so if we, solar and wind will be something we definitely will use in the next several decades. And also, so what are the low carbon solutions that can work with renewable to replace dispatchable fossil fuel generation? So answer like energy storage was one of the promising solutions there. So, they are started to show, like how much energy storage, like in terms of power generation capacity, we need to decarbonize or deeply decarbonize power system. So in general, it started showing like about like more than 50% of the peak power. So which in the UK, something like more than 30 gigawatt hours, which aligns well with what I just estimated in the past, which is close to the gas power generation. So that's for the power. So how about energy storage capacity? So definitely there are also a number of studies. So one study here I show here. So it's also analyzed the maximum required storage duration, for the energy storage when you, gradually increase the decarbonization of the power system. In general, like the storage duration actually rapidly increase when you're towards the highly deeply decarbonized system. And so overall, so we need a significant skill in terms of both power and energy storage capacity, to deeply decarbonize our power system. So the second question I want to, talk about more about what are large-scale electrical energy storage and how to use them. The first question probably, the first previous speaker gave a very good introduction of the analysis of all the energy storage technologies, particularly for the mechanical thermal energy storage. So here, like, I roughly classified all the storage into three categories, so like mechanical, electrical, chemical, and also alternative fuel-based, or like power to fuel-based energy storage. So here, like, I don't want to give a detailed introduction, but in general, as Yongliang mentioned, so it's more about decoupled energy and power storage. You have a storable carrier. I call something like reservoir-based storage here. And for the electrical, electrochemical cells to generate electricity. By among all the technology, you can find flow battery also one type of the reservoir-based storage, which has decoupled energy and the power generation. So for the power to fuel, more general, because the fuel is more, when I say it's a fuel, so it should be easily to transport. It could be used at a very big scale system and globally transportable, so which will probably have impact beyond electricity. So if we look at technical, performance or in terms of power rating and the time scale of the service, which is more about discharging duration. As I said, so the large-scale energy storage may need very longer duration, larger power capacity. So that basically there are a set of technology may be suitable to be used for the large-scale electrical energy storage. And but the problem is, if you want to really use it in the practice, technical is one point. So it's more about cost. So there, and also as previous speaker mentioned, so like in terms of energy cost and power cost, you can characterize energy storage technology But we also need to think about, how because depend on how you use the energy storage, the cost will be different. And also important to know like how this large-scale electrical energy storage would impact the cost of the whole system. So that means we need to also do the whole system analysis with renewable and energy storage. So here is one example of how I did, to do a kind of solid experimental to see, how I can use compressed air energy storage as a large-scale energy storage to decarbonize like UK power system. So this is a figure which is similar to what I showed previously. So it's a current UK power system like significantly rely on gas-based power generators. So what I did, so first I increase the solar and wind power to a sufficiently energy capacity to replace current gas power generation. And then I surveyed data like of all the existing underground storage caverns, which could be useful case as large scale energy storage. And I built a model and optimized unique commitment and economic dispatch of all the generator and storage in that scenario and analyze the cost and the carbon emissions. So I would to like step by step, to see how it works and what's the result. So the first, in the UK, like currently there are like 13, announced or in use underground caverns. So most of them were used for store natural gas, and also you can see in the figure on the left-hand side. So most of them actually in England, and they have different capacity and different like operating parameters. So with all these parameters, so what's in step 2? So I use our model, like try to estimate what's the storage capacity for each of them if they are used for compressed air energy storage, and I estimate what will be the round trip efficiency in terms of both electricity and thermal energy storage. And with all this data, I built a model and mix the integer linear programming model, try to integrate all the generators, solar, wind, and the gas plants, and also as well as compressed air energy storage to do hourly based analysis, to optimize the dispatch of all the components and to meet the like hourly demand. And then so there will be like 3 scenarios as set in the analysis. So first one is the current UK system. The second one, like as I said, like sufficient solar and wind to replace gas boiler in terms of energy, but this one without the large scale energy storage. The third one is a low carbon system with both renewable and the large scale energy storage, which is compressed air in this case study. The result showing here, like with all this, using all these existing underground caverns, and for compressed air energy storage, we can significantly reduce the carbon emissions, like from current like more than 60 megaton per year to about slightly lower than 10 megaton per year, which about 85% reduction. In terms of cost, the total system cost like from something like mean cost from about $84 per megawatt hours to around like $108 megawatt hours, which also like around 20 like percent increase. And if you look detail at how all the different types of how these sites are used for in terms of duration. So some of them used for intraday storage, and most of them are used for like longer duration, which from 1 day to 5 days. So the hour like up to 100 hours. So in general, the conclusion, of this study, like the thought experiment should demonstrate use of compressed air with underground store caverns could provide flexibility at a large scale, hundreds of gigawatt hours over duration from hours to days. So at a plausibly affordable cost. So but in practice, we won't use compressed air energy storage as a single technology to meet all this. And there is a portfolio of large-scale energy storage could be used to fill the storage gap. And this is a recent study showing kind of in different scenario how large-scale energy storage could be positively affect the power system for reducing the cost. So depending on the the cost of the storage and the non-gray area, which means the design space for the large-scale, long-duration energy storage, which could provide cost reductions compared to other solutions. But in general, different technology have different opportunity window actually to positively impact the power system. So the third one, I want to briefly talk about the challenge and opportunities. So this is basically what our current electricity market looks like. Basically, we have energy market, capacity market, and ancillary services. And also there are growing kind of support, financial support from public funding and private funding. And if you look deeply at what's this revenues, for different parts. So like ancillary, lithium-ion battery will be something like mostly used for ancillary services. And for energy market and capacity market, actually fossil fuel gas, fossil fuel generator and low carbon generator, are mainly the kind of the player in the market. So people may always think like, for example, large-scale energy storage like compressed air, actually compete with lithium-ion battery. But the fact is, I would say it's so for such like large-scale energy storage, they may not be suitable or very suitable for the ancillary services. Mostly they actually provide energy, in the energy market. So actually they are kind of more, I would say, usually compete with fossil fuel generator or low carbon generators. But compared to this, generators, their marginal cost to generate, for example, 1 kilowatt hours electricity actually is very low. Compared to you need to build a brand new large-scale energy storage. So that means the business case for the large-scale energy storage actually is not very good at the moment. So, but there is a growing momentum actually to support building new large-scale energy storage. And in the future, probably with increasing support for the low carbon infrastructure and also the reformed electricity market. So besides the increasing support for the new technologies, I think one important opportunity or the way for large-scale energy storage is to find specific customers, which allows them actually to have the business case in each of the market. Because currently, although the system benefits provided by the large-scale energy storage actually has wide recognized by different people, but actually there's no a clear route to market for, I would say, to have better economics or a good business case for this technology to be used in the real world. Okay, that's all my presentation. Thank you for your attention.
Thank you, Dr. He. So if there's any question from the audience, please type your question just on the right of the screen. So Dr. He, I just have a quick question. So so you mentioned you use compressed air energy storage. So can you let us know the basic payback period? So for such a, because I find that no, this kind of technology need a high investment. So have you got any data or analysis on the payback period?
Yeah, I think I think I do not, for the simple answer, I don't have an exact number for that, but I think it also depends on, as I said, in different business case, you may have different support. And if at a different scale, compressed energy storage also have some small scale applications. So that means depending on different, application, you may have different, revenues, different kind of, I would say, business model to pay back your capex. So in general, compressed energy storage, if we talk about large scale energy storage, so it's a very capex intensive system. So you need to invest a lot at the beginning to build a system, and then you through the kind of in terms of different markets, some markets like, for example, like China, probably they have support from government try to help you maintain the cash flow. But for example, in the UK, you probably need to compete with other generators in the market to gain your revenue. So it's difficult to say, what's the exact payback time. But I would say, in the UK, potentially, it looks like the economics is not very good.
Okay, thank you. So I think there are two more questions for you. Maybe we do not have time here, but Dr. He, if you can type your answers, or maybe you can answer these questions after the session. I mean, it's a breakout discussion. Okay, thank you again, Dr. So our final speaker of this session will be Corentin Jakovic, if I say this correctly. So Corentin is currently a PhD student at Ulster University, and his interest is around the smarter operation of low carbon technologies to enable sustainable energy transition. So Corentin, are you there? Yeah. So
hi, yeah, I'm here.
I will speak to you now.
Let me share my screen. Okay, I hope you can see the slides here. Does this work?
Yes, you can see it.
Yes.
I just wanted to stop my video to make sure the internet connection is fine. Okay. So thank you very much for the nice introduction. Today I'm going to talk to you about battery storage control methods for the electrification of heat and transport at the domestic level, which is essentially going to be sort of the small scale version of what we've seen in the past two presentations. So this presentation is going to follow a very classic structure. I'm going to start with a brief introduction, talk about the methodology that I used in my research, and I'll develop on 2 case studies and finish with a brief conclusion. So as an introduction, a lot of things have already been introduced in the great presentations we've had so far. And I'm just gonna give a bit of context and background by going back to the title of my presentation and explaining some of the key terms. So obviously, electrification of heat and transport, it's sort of one of the main topics of today's chat. Those two sectors are very large CO2 emitters, so their electrification could represent a very strong decarbonization. And we've also seen that storage could be very important in the sense that unsupervised electrification of those sectors could cause a real threat to the electricity network, which was not originally designed for such a demand. So I'm focusing on the domestic level here, small scale, as I said. Why this choice in particular? Well, it turns out that according to the literature, when looking at storage and how they could provide the services that we're looking here, the closer to the loads, the better. So connecting storage at the domestic level seems to have a greater potential to provide all those services. And finally, about control methods. What I want to emphasize here, and it's essentially the core of my research, is that it's not just about placing storage here and there in the network. It's also a lot about how do you control them, what do you tell them to do, because the result in terms of the efficiency and the positive impact on the grid is highly dependent on this factor. Let me move on to the methodology. Obviously, the first key element was for me to build a battery model. As you will see later, that there was a lot of simulations that have to be run. So I needed a battery model that was light enough to be run a high number of times. So a mathematically simple model. The one I chose is called a bucket model, which essentially just describes the flows of energy in and out of the battery. The energy stored in the battery and takes account for some conversion losses. And that's pretty much it. So obviously this model was validated against but it remained very simple. So with this model up and running, I then needed data to run this model on. So what I did is I used a tool developed at the University of Loughborough, the Crests profile generator, which is essentially, which allows essentially to generate electricity demand profiles and PV generation profiles occupancy profiles, and a lot of very nice things at the domestic level, just in a few clicks and with a very good accuracy, very good resolution, sorry. So you have a few examples here. I also use this tool to define a heat pump model, essentially by modifying the building thermal model that was the profile generator. I also used it to define my electric vehicle model by using the occupancy profile in order to determine when electric vehicles are at home and charging and things. I also needed an electricity network to test all my simulations. So the one I used is a real network. You can see a graphical representation here. It's located in Northern Ireland in Glenvarra Drive. So that's it's a low voltage network, 3-phase, and it has 203 residential customers. And I used OpenDSS in order to model this network. So from now on, every time I'm going to talk to you about simulation results and things like that, this is always happening in this network. Finally, control methods. As I said in the introduction, control methods are key in achieving performant storage control or operation. I could talk forever about control methods, but at this stage, I'm just gonna explain that there's two main categories of control methods. And to illustrate this, here is a very simple electricity network, and you can see with some storage, so residential storage units here in green. The first category is coordinated approach. So in this case, you have essentially an aggregator which takes control of the batteries, and in order to make them cooperate to achieve a certain objective. The second option is uncoordinated, and in this case, each battery is essentially operating on its own. It doesn't communicate with the rest of the grid, and it just focuses on local measurements to base its operation. So at this stage, you may think that uncoordinated approach is way less efficient than coordinated approach because it doesn't have this cooperation feature. And you'd be right thinking this. The only thing is that nowadays, with domestic storage, the uncoordinated approach is vastly used in the majority of the cases. So it's still very important to study it. And it's mostly due to the fact that it's so much simpler to implement because it doesn't need all these communication between units and so on. Okay, so let me move on to the first case study, which is about electric vehicles. And as I said in the introduction, unsupervised charging of electric vehicles can be very detrimental to the electricity network. And this is illustrated here in this graph where I run my EV models on the network that I used earlier. What you can see is that at higher and higher EV penetration, so for example, 25% of electric vehicles, houses with an electric vehicle in the house, that's the pink curve here, 50%, 75%, and so on. You can see that as the number of electric vehicles connected to the grid increases, you have a higher and higher peak whenever those electric vehicles are charging. This is up to a point where you have actually a multiplication by a factor of 4 in the energy demand, which is obviously could be very detrimental to the network. So on the other hand, 100% penetration of EVs is not very likely to happen in the near future, but still, it still means that if we're going to be serious about electrification of the transport sector, there's going to be measures to be taken in order to avoid dramatic problems like this one. So what do I propose in order to avoid such problems? Control methods, so controlling those batteries in a smart way. I'm going to briefly introduce here 4 of those control methods applied in this case study. The first one is uncoordinated approach using residential batteries. So essentially this approach consists in having a residential battery which supports the charging of electric vehicles. So as it's uncoordinated, those batteries don't communicate with each other, they just focus on their own individual EV, and that's all they do. This is as opposed to obviously uncoordinated approach, the second one, which I introduce here. This time you have an aggregator which takes control of those residential storage to in turn support the charging of electric vehicles. What I also implemented is a direct control of EVs. So this time, rather than having residential batteries, we directly control the battery of the EV, and this was mentioned, I think, in one of the previous talks. There's a very great potential in working like that. So in the uncoordinated approach, the EVs simply try to charge in a smarter way on their own without communicating with the rest of the world, simply, for example, at lower power rate, things like that. In the coordinated approach, this time you have an aggregator which directly takes control of the charging of the EV, again, in order to reduce the impact. So what are the results that I obtained with these methods? This is a type of graph that I obtained after running the simulations. It essentially compares the 4 control methods that I introduced, colors here, compares them with the unsupervised charging, which is sort of the worst case scenario that I introduced at the beginning of this case study. So it's in gray here. And it also gives the case without EVs, so sort of like the base case, which is given here as a reference point. You can see here, as I mentioned, that depending on the control method that you use, so the different colors here, you have a completely different result on the resulting power demand on the grid. So this is a winter month and summer months, by the way. What else can we say? We see that for all control methods, there's a reduction in peaks. So the maximum value essentially is always reduced to a different extent, depending on the control method, but it's always improved. We also have a decrease in reverse power flows. So this is visible here. These are essentially the negative values in the summer months. They correspond to times where you have excess PV on the grid, which is not absorbed directly. So it's exported back to the rest of the grid. That's something that transformers usually don't really like when it happens to a larger extent. The overall consumption is not directly visible in this graph, but what I can tell you is that when directly controlling EVs, the overall consumption was reduced. And that's important because the overall consumption is essentially the electricity bill at the end of the month for the customers. On the other hand, with residential batteries, there was a slight increase most of the times in there was also a reduction in losses. Again, not directly visible here, but you can infer this by looking at the reduction in peaks particularly. And as a conclusion of this case study, the direct control of EVs proved to be a better performance to have results on the grid rather than controlling residential storage to support the EVs. Also, a very important thing here is the fact that in the morning, the state of charge, so SOC stands for state of charge of EVs, was essentially left unchanged. This is a very important result because it means that when the customers wake up in the morning, their EVs are ready to be used. So a smart control of their EVs doesn't change or doesn't alter the use as a vehicle, which is the primary use. A second case study, I'm conscious of the time, so I'm not gonna go in a very great level of details with this case study, but essentially I did exactly the same thing as what I introduced with EVs by just replacing EVs with heat pumps and looking at the results. So the starting point here is to establish that, again, heat pumps integrated to the network without any additional measures can be very detrimental. This is very similar to the graph that I introduced at the beginning of the previous case study. And it shows that as you increase the level of penetration of heat pumps on the grid, you increase demand on this grid, which can be detrimental up to a certain extent. So for this one, I developed 7. Yeah.
Sorry, I might need to stop you. We have not really understood the last slide because you were cut off. Is it?
Oh, okay, sorry.
Is it
this one?
Your headphones or something?
Is it clear now, the sound?
It's just it's like in your graph. Sometimes it's on and sometimes it's off, I think.
I'll try maybe to speak a bit slower. So I'll start again in this slide. That's the beginning of this case study, and as I was saying, it's just to show, as for electric vehicles earlier, when you increase the level of penetration of heat pumps on the grid, you have a greater consumption, which to a certain extent can be bad to the electricity network, because it essentially means that the network is going to suffer from higher demand, higher flows of power. So I'm not going to go in the detail of the control methods that I used here because there are many of them and they're would take a long time to introduce. I'm just going to show some of the results. I'm starting with the self-consumption algorithm, which is one of these methods. It's an important one because this method is essentially the most commonly used today out there to control, batteries in the real world. Not necessarily with heat pumps, but in general, this method is used extensively. And what you can see on these graphs is, well, essentially you can't see anything. This is a big problem because it means that if we continue operating batteries the way they are operated today, they won't have any impact, at least on the integration of heat pumps. Another control method consists in charging at night time, taking advantage of cheaper tariffs, as some of them were introduced earlier. So essentially, this is still an uncoordinated approach. You can see some level of improvement here. You can clearly see that during the nighttime, there's some charging of the batteries with those blocks of charging here, but still only a slight improvement. The final one, this one is a reference state of charge algorithm, a bit more funky. You can see that in the results, there's a slightly smoother consumption profile. But again, the results are still very close to the net demand, which doesn't include the operation of batteries. This is as opposed to when you look at coordinated control algorithm. And this time you can really see a net improvement comparing to the previous results. So this time you have the demand, which is clearly flattened and it looks very nice and controlled here. So this really shows that for the integration of heat pumps anyways, a coordinated control will provide much better results. So I think it's time for me to conclude. A few key points. So as I said in the introduction, electrification of heat and transport is essential to reach net zero or sustainable economies. But if unsupervised, they could be highly detrimental to the grid. So this is where storage and plays an important role for the electrification of transport. It seems that simply directly controlling electric vehicles can show a drastic improvement in the results that we obtain. And for the electrification of the heat sector, at least for heat pump integration, more complex and more coordinated algorithms are required in order to have substantial results. So thank you very much for your attention. I hope the sound was not too bad towards the end and that you were able to understand something.
Thank you very much, Valentin. A nice talk. So I think we have a question from the audience saying if there are different control strategies on different impacts on the lifetime of batteries. Yeah, I think there's a kind of question about the operation control. You can see the questions, Valentin.
Sorry, I didn't quite understand the question.
Yeah, so Dr. He just say, will different control strategies have different impacts on the lifetime of batteries?
Oh yeah, yeah. This is a very important point indeed, and this is something that's very important to consider. Of course, it will have an impact on the lifetime because the way you operate the battery makes it charge at higher or lower rates, or stay at a very different level of state of charge. So for those of you who are familiar with this, depending on where you are in these quantities, you can have very different level of impact on the lifetime of batteries. So this is something that has to be considered. It is usually implemented in simulations. This is not something I was specifically looking at in my own project, but I'm definitely aware this is something that's a key element, especially regarding the high investment costs of batteries. You definitely want them to last long.
Okay, thank you. So I have a short question for you, Valentin. So when you analyze the EV battery, you consider the charging. I mean, I know you compare the winter and summer time. So I wonder if you consider the battery performance itself, because I know during winter and the summer, the battery performance will be different. I mean, the battery efficiency will be different. I don't know if you take this into consideration during your work?
So this is also a very interesting point, but this was not included in those simulations here. So I sticked with the very simple battery model that I introduced at the beginning, which just accounts for the energy transfers essentially. No, this wasn't something included in the simulations, but I admit that this is something that has to be looked at. Yes.
Okay, thank you, Corentin. So
thanks.
Thank you very much. Thank you for your talk. So yeah, so I think it's time for me to close this session. So thank you for all the three speakers, and thank you for everyone. Thank you for questions from the audience. So I think it's time for us to have a 10 minutes coffee break. If I'm correct, Lumina. So I think we can come back at around 11 o'clock, and we'll start the second session. And the second session will be chaired by my colleague Hui. So thank you, everyone. So now I think we can have a coffee now.
Hello, everyone. I hope you are all having a good coffee break and are ready for the next 3 excellent talks. So our next speaker would be Dr. Reshma Rao from Imperial College London, and she's going to talk about the rational design of a nickel-based catalyst for electrochemical water oxidation. So Reshma has completed her PhD at MIT in 2019, where she worked with Professor Yang Shaohong on understanding the fundamental processes that occurred at the oxide-water interface under electrochemical conditions that are relevant for water splitting. So since January 2020, she has been a research associate at Imperial College London and currently working with Professor James Durant and Dr. Evan Stevens on spectral electrochemical studies on photo and electrochemical interface for the conversion of renewable energy to high-value fuels and chemicals. So Reshma, the floor is yours.
Thanks, Hui, for the introduction. Hopefully you can see my slides and hear me fine. Okay. Yeah, it's really exciting series of talks, and I'm happy to be a part of it and talk slightly about how we can come at these challenges from a materials perspective to design better catalysts to enable us to get to this net zero ambition. So we've heard a couple of times already today that with our kind of baseline situation, we're going to see a huge increase in the CO2 emissions. And if we want to stick to this kind of temperature rise of 2 degrees, we need to significantly reduce the carbon-based emissions that we have relative to what we see today. And one way to achieve that is by using hydrogen to substitute our kind of fossil-free based energy sources. And hydrogen is particularly attractive because it can be used across a variety of different sectors, from industry to transport, as well as heating for domestic use. But when we look at the numbers on this graph here, it's a bit daunting that relative to today, we need to increase the amount of hydrogen we produce by about an order of magnitude. So that's a huge kind of challenge that we need to overcome in order to make this hydrogen-based economy a reality. So one way of thinking about producing hydrogen at scale is using low temperature water electrolysis, which basically relies on earth abundant resources of sunlight and water. And the way we can carry out this electrolysis is that we have 2 different electrodes, an anode and a cathode. At the anode, we produce oxygen, and at the cathode, we produce hydrogen. So while hydrogen is the gas that we're really interested in, if we look at the energetics of the overall reaction, we see here that the oxygen evolution reaction basically has the significant amount of energy loss that occurs during carrying out this reaction. So then the materials-based challenge remains to try and figure out materials that can catalyze this oxygen evolution reaction at a faster rate and basically reduce this overpotential that's required, especially at high current densities for overall water splitting. So in the last 10 years or so, people have been looking at a variety of different catalysts. And here's basically a summary of some of the real state-of-the-art catalysts for the reaction. So here you have the turnover frequency, which is an activity metric, and at the bottom are the catalyst compositions. And what's quite interesting when you look at them is it stands out that a lot of them are based on doped nickel-based oxides or oxyhydroxides. And so this makes nickel a really attractive materials choice for some of these catalysts. And apart from being really active, one of the other kind of attractive properties is that nickel is quite widely abundant, and the price of nickel is relatively low compared to some of the other kind of precious metal catalysts out there. And if we want to scale up to the terawatt scale, then it's important to look for these materials that are relatively earth abundant. So what we want to do in the next few slides, what I'll be doing is kind of summarizing one kind of study that we've been looking at on these kind of doped nickel oxides to try and understand from a kind of fundamental scientific viewpoint why these catalysts are so good for this particular reaction. So in order to do this systematically, we started with a series of doped nickel oxides ranging from manganese, cobalt, iron, and zinc doped oxides. And if you look at some of these catalysts on the left, it's just a photograph of them. And then if you look at them under a microscope, you see they have this really foamy morphology. And what's quite surprising is that if you look at the electrochemical performance, just with 10% doping of these different metal ions, you see you have a really wide difference in the catalytic activity, being significantly higher for the iron, followed by the cobalt, manganese, and then the undoped and the zinc doped oxides have really low activity. So in order to try and understand these trends, what we need to do is try and see how these materials evolve under electrochemical potentials, specifically under oxidizing potentials where these reactions happen. So based on literature, we know that as soon as you dip this nickel oxide in a solution, you have these hydroxyl groups that are present on the surface. And as soon as you increase the potential slightly, you have the first deprotonation of this OH group to form oxo groups on the surface. And you can see this redox reaction here, specifically in the case of the manganese doped oxide, where you have this really strong redox peak, which is shaded here just prior to this kind of catalytic current. And looking at this redox peak for all the different series of oxides that we've studied, we see that going from the manganese to the zinc doped oxide, the position of this redox peak progressively increases to higher potentials. And what that implies in terms of these materials is that, for example, in the zinc doped case, the binding energy of this oxygen is really weak, and therefore it takes a much higher electrochemical potential to form this oxyhydroxide phase in the case of the zinc doped catalyst. We can also spectroscopically probe these different redox reactions. So for example, if we were to scan across this redox phase here, we see using UV-vis spectroscopy that we have a characteristic spectra evolve with a shape like this, with a peak at about 450, 500 nanometers. Interestingly, if we polarize the electrode to higher potentials than this going into the water oxidation regime, we see that we have a distinct spectral shape appear at which has a peak at much higher wavelengths. And what this implies is that you have a distinct oxidized nickel species forming at higher potentials. We can also kind of quantify the density of these species. So as we increase the potential from about 1.5 to 1.6 volts, we see that the density of these second oxidized species increases as a function of potential. So while this is specifically an example of the manganese doped nickel oxide, we see that across the spectrum of catalysts that we've studied here, we have a similar growth in these species as a function of potential. But what's different is that in the case of the manganese doped oxide, these are formed at relatively low potentials of about 1.5 volts, whereas looking at the zinc doped catalyst, you need about 200 millivolts higher, about 1.68, 1.7 volts to trigger the formation of these oxidized species. We can take all of this analysis one step forward, and I won't go into the details of how exactly we do it, but you can convert this data into a quantitative density of oxidized species as a function of potential. And like we've seen before, in the case of manganese, you have these species forming at a much lower potential compared to the zinc and the undoped oxide. So based on all of this information, what we can do is also quantify a turnover frequency, which is an intrinsic measure of the amount of oxygen that's produced per density of these oxidized species per second. And interestingly, here again, we see that the iron doped oxide has much faster kinetics at a given potential. And while it's the manganese doped catalyst that can produce these oxidized species quite readily, its intrinsic kinetics to oxidized water is much slower. And in order to then try and understand why we have these trends as a function of dopants, what we can do is perform a rate law analysis. So quite simply, a rate law analysis relates the rate of a reaction, which is the current in this case, to the density of the active species. And the active species are raised to the power of alpha, where alpha is then the order of the reaction with respect to these active species. So using quite a straightforward kind of mathematical manipulation, we can see that if you were to look at the log of the rate versus the log of the density of these active species, the slope of that graph would then give you the numerical value of alpha, which is basically what we've done in the next slide here. So we can see on the y-axis, we have the log of the current density, and on the x-axis, we have the log of the oxidized species. And across all these different catalysts, we see that we have an alpha value of about 2. And what this tells us mechanistically is that it's possible that the rate determining step for this reaction involves kind of the chemical coupling of these two oxo species on adjacent nickel sites to form a molecular oxygen. So we've gained a lot of kind of mechanistic insight into how these different catalysts oxidize water into molecular oxygen. And if we put all of that together, we can come to a concise picture, which looks something like this, where you have these hydroxide groups bound to a nickel center. As you increase potential, we see we have a growth of these oxidized species, which we've detected using UV-vis spectroscopy. So we are forming these oxo groups on the nickel center. And based on the rate law analysis that I just showed you, we can see that we need 2 of these different oxo species to chemically come together to form one molecule of oxygen. And that returns back a vacant nickel site on which you can again find OH- groups from solution and continue the catalytic mechanism. So based on this proposed mechanism, we can explain why we have different trends as a function of doping. So for example, if we plot the turnover frequency as a function of the redox peak potential, which is basically a proxy for the binding energy of oxygen on these different doped nickel sites, what we see is we have this characteristic volcano shape. So going from iron to the manganese doped case, we can see that we know that the manganese binds oxygen too strongly, so it's quite easy to form these oxidized species, but this final oxygen removal via this OO coupling is what probably limits the overall rate of the reaction. On the other hand, on the other leg of the volcano, going from iron to zinc, we know that it takes a huge amount of electrochemical potential to form these oxidized states on the zinc dope site. So in this case, you're basically limited by this potential limiting step of forming these oxo species. And iron is then on the sweet spot of this volcano where it binds oxygen neither too strongly nor weakly, making it a kind of ideal catalyst. So if we wanted to find new catalysts, we're looking basically at this region between the iron doped and the undoped nickel oxide, where we believe that we have more active catalysts in this material space. So the final thing that we wanted to do is see how valid this learning was, which is in a really lab scale setup to actually kind of a more industrially relevant catalytic structure. So we then deposited these catalysts on a 3-dimensional nickel foam, which would be something that would be more applicable to large scale water electrolysis because you have this really larger surface area of the nickel foam. And what's quite interesting to see is that the same activity trends that hold at the lab scale, where we had deposited this on kind of ideal substrates where we can look at all of these fundamental studies, holds true even when you have these 3-dimensional nickel foam structures. And quite interestingly, we have to achieve 10 milliamps per centimeter square, which is kind of the current density at which people benchmark these catalysts, we need an overpotential of 250 millivolts, which is quite close to state of the art for water oxidation materials. So that brings me to my conclusion. So hopefully I've convinced you that we have a fairly bright future in terms of looking at hydrogen as an alternative energy vector. And low temperature water electrolysis is one way of getting there, but we're really limited by this oxygen evolution reaction that occurs at the anode. And using some of the spectroelectrochemical techniques that I've showed you, it's possible to rationally try and understand why some materials perform better than others, and then try and develop new catalysts for this reaction. So with that, I'd like to thank both our funding bodies and all of the different people who've been involved with this research at Imperial College and a lot of our collaborators. And I'd also like to thank you for listening, and I'd be happy to take any questions now or later in the breakout rooms or via typing on the message.
Thank you, Rashma, for the very, very nice talk. Audience, I just remind you, like, if you have any questions, just type in the chat, and we will have the speakers answered now or in the breakout rooms. So I have a quite small question for Rashma. Like, when you have those dopants, do you have some idea where they have been doped in the nickel hydroxide structures?
So we don't know exactly which site in the crystal structure it occupies, but it's quite homogeneously throughout the material. It's not like specifically segregated to the surface or in the bulk. It's quite homogeneous.
Okay, I see.
I have a question, Rashma. What is the front slide of your talk? What did you show there?
Oh, it's hydrogen being produced on just a metal wire, and the background is all fancied up, but yeah.
And maybe a bit more into the first session, let's say, of things. Do you think it's only in the catalyst development that we have to push hydrogen, or is it like a bigger obstacle, let's say, in general, how to push the hydrogen economy?
No, I think even in terms of electrolysis, I think there's a lot in like membrane design that we still need to figure out. Especially if you look at PEM electrolyzers, I think there's a lot about support. So we don't have even good supports to put these catalysts on once we figure out the best catalyst. So there's a lot to go in that area. And then with hydrogen transport, I think there's a huge materials challenge even with that, how we are going to transport all of this hydrogen. But yeah, I think it's much more than just the catalyst materials, I think. But
thanks.
Yeah.
We have a question from Edward. So do you have some idea of the durability of these materials?
So we haven't done super long-term durability measurements. We've done like the 24-hour measurements, and the durability is quite good. But obviously, I think that's another gap to try and figure out how you can extend that kind of 24-hour analysis to thousands, 10,000s of hours with startup shutdown kind of modeling. But it's fairly stable, but I'm not sure how that translates to kind of the real world large scale applications.
Yeah, I see. Okay, I think in the interest of time, thank you, Rashma, again for the talk. And we welcome our next speaker, Dr. Edward Brightman from University of Strathclyde. And his talk is on electrochemical engineering of energy storage. So Dr. Edward Brightman is a lecturer at the University of Strathclyde in the chemical engineering department. So he has worked on the electrochemical energy conversion and storage technologies since his doctoral study at Imperial College. And he has subsequently worked at the National Physical Laboratory and also as an R&D manager for fuel cell startup before coming back to academia. So he specialized in the development of innovative technologies for in situ measurement of performance, degradation, and model validation. So he's also interested in the engineering level novel electrochemical devices and his experience with fuel cells, electrolyzers, redox flow batteries, and the lithium-ion batteries. So Edward, hand on to you.
Thanks very much, Hui, for the introduction. I hope you can all hear me and see my slides.
Yes.
So yeah, I'll just sort my screen out so I can see everything that I need to see. Yeah, thanks for inviting me to join this this symposium. I think I kind of only just qualify as an early career researcher because I sort of rejoined academia about 2 years ago, and before that I worked for a startup, and as you mentioned, I worked at the National Physical Laboratory. So my interest is kind of quite wide in electrochemical energy storage and hydrogen, and I'm going to give a bit of an overview of all of the projects that I'm sort of actively getting started since I joined the department here at Strathclyde, and maybe go into a little bit more detail on one project in particular. Okay, so I probably don't need to talk too much about the rationale for this work because it's been very well presented by previous speakers this morning. But obviously we're all doing our best to try and address the climate emergency, and luckily there's some legislation that's helping us along the way and lots of good work going into that. But one of the big challenges that's been mentioned a lot, and which is probably the biggest motivator for this network, this supergen network, is the need for enabling more electrification with wind and solar renewable generation. But obviously we need to store some of that energy so that it's available when it's needed. And so energy storage is one big interest of mine, and hydrogen is also a big interest of mine. My background is sort of more in hydrogen and fuel cells, but I've since more recently become more interested in flow batteries. So I've worked, as I said, with polymer electrolyte membrane fuel cells and electrolyzers, and a bit with solid oxide fuel cells. And I'm also interested in flow batteries because there's a lot of similarities in the kind of scientific challenges, things like mass transport and catalysis, where some of the insights and knowledge from the fuel cell world can be translated and applied to engineering better redox flow batteries. But for all of these technologies, and I think it's been mentioned quite a lot this morning, one of the biggest barriers is cost to getting these widely deployed, and at the root of the cost challenge are the questions of durability and performance. So my sort of research background, starting at NPL and since then, has been trying to look at this in terms of understanding degradation mechanisms to try and improve durability, and also developing in situ measurement techniques to understand performance and try to optimize the performance of these devices. But more recently, I've become interested in engineering novel devices and sort of trying to get new concepts to a demonstration stage. So I've got quite a lot of projects potentially in the pipeline with industry here at Strathclyde to that end. So I'd like to introduce the team at Strathclyde. There's actually a group of us here working on electrochemical engineering. So we have Professor Roy, whose background is in electrodeposition. So she comes to electrochemistry from more of a sort of manufacturing point of view, and her colleague, Dr. Todd Green, also has a background in corrosion and deep eutectic solvents. And then we've also got a newer member of the academic team, Dr. Dragos Nigu, who joined us from St Andrews and Newcastle, and he's an expert in nanomaterials, particularly for solid oxide electrolyzer and fuel cells. So we have a postdoc, as well, Dr. Shahin Nickman, who's got a background in flow batteries, and he works for me on one of the projects that I'll be talking about in a moment, and several PhD students. So the first project I wanted to just bring to everyone's attention and talk a bit about is ongoing. This is a Faraday Institution project, which I was very lucky to get involved with. So I'm the PI on this project, working closely with Storterra, who are developing lithium polysulfide flow batteries. And some of the challenges for this technology are developing the chemical solvent system for the liquid electrolyte so that it's stable, and improving the actual materials of the electrodes so that they can perform better and be used in a roll-to-roll manufacturing process to manufacture these at scale. And the potential for this technology, this lithium polysulfide technology, is really quite impressive in terms of reducing the cost of energy storage. And we have some targets for this project. And not only the cost can be lower, but we can use recycled lithium, and obviously sulfur as a raw material is very cheap and widely available. But also it's safer than conventional lithium-ion batteries. So the motivation for this project and the funding for this project comes from the UK aid budget before that budget got slashed by the current government. So we were lucky to get in just in time for this. But the motivation for this is to deploy these batteries in developing countries where there's a need for low-cost energy storage to work alongside solar energy generation to bring electrification to especially rural communities where especially in sub-Saharan African countries, there's very poor access to electricity. And this is a great humanitarian scandal, really, in terms of international development. So I'm working in partnership with the Electrical Engineering Department here at Strathclyde and the Power Networks Demonstration Centre, which is also linked to the university here. And we're doing some techno-economic modelling for this project. Part of that is to compare the likely cost of storage with the incumbent technologies, which are mainly lithium-ion and lead-acid. And then there's also a sort of chemical and electrochemical development work package, which is developing the electrolytes that I mentioned, and also developing the graphite felts and the electrode materials. So this is about 6 months into a 2-year project, and so more results will be forthcoming. And I'm sure some of you might be involved with Faraday Institution already, and there'll be more to present on this at the November conference. So the second project that I wanted to talk about, this is actually the one that got me involved in the Supergen Energy Storage Network, which I'm really pleased to be here talking about today. This is a zinc bromine flow battery, which the universities come into possession of, kind of through serendipity, but this was supplied to us by Lotte Chemical for a previous project a few years ago, and then Lotte Chemical decided to give it to us. And it's a 25 kilowatt, 50 kilowatt hour prototype zinc bromine flow battery. It's a single liquid flow battery, which means that the zinc anode is a solid metal plating anode, and that's a similar configuration to the lithium polysulfide battery that I was talking about a moment ago. So this has a bit of a history to it, and the project was supposed to start earlier this year, but we're having to relocate the battery from where it was originally planned to be installed up in a rural community in Scotland. We're bringing it onto the university campus here in Glasgow. So it's going to be installed next to one of the university buildings, which means that we can have much more physical access to it, which is great from a research point of view and a training point of view. And it'll also make it a great showcase for the university. So here's a picture of the inside of this system. We have 4 stacks, 4 zinc bromine stacks, and the catholyte liquid is stored in these tanks underneath. And this was tested at the Power Networks Demonstration Centre a few years ago to get some performance data. And the project that that will shortly be starting, which is funded through the Energy Storage Network, is aiming to develop smart control algorithms and also diagnostic methods from this battery. So once it's installed, it's going to be linked up virtually with some rooftop solar generation that the university's got installed on some of the buildings here on the campus, and we're installing a lot more over the next few months. So this is a great opportunity for getting some real world, real usage data for model validation and for developing these control algorithms. So I'm really excited and can't wait for this project to start. I think I'm conscious of time, so there's not too many slides left. This is another project which is sort of happening in the background. And in terms of materials, this is quite interesting because it's working with a company that's trying to develop safer and environmentally benign redox active electrolytes for flow batteries with a view to reducing the cost of materials, but also making electrolytes that are non-corrosive or at least less corrosive, so they can be used and stored in stainless steel containers. And also the organic redox flow battery materials are much cheaper than the sort of heavy metal vanadium type. So that's just a minor project that I wanted to mention. Finally, because this session is all about materials, I wanted to talk about one of my PhD students' projects, which is developing nanostructured tungsten oxide materials for supercapacitors. And tungsten oxide has some really interesting redox properties. It has quite fast proton intercalation kinetics with an electron reduction step to form this tungsten bronze material. And it comes in several different crystal polymorphs. So the most active for this, this reversible reduction and oxidation mechanism is found to be this metastable hexagonal phase. And so the challenge is to synthesize high surface area tungsten oxide with this hexagonal phase reliably and reproducibly and in enough quantity to make an energy storage electrode. And the main aim of this project was to try to grow this material directly on a tungsten foil substrate, because that way, so this is the methodology, we would start with a tungsten foil and we would create a seed layer from acid treatment, and then in a hydrothermal step, we would generate this hexagonal tungsten oxide with a high surface area nanostructure in very few steps. And the idea is that this reduces the number of substrate materials that we need and possibly allows for a cheaper device. So we've had some success with this. We've managed to create some of these deposited foils and got some results from this. And the next step is to try to compare the performance of this, create an actual supercapacitor device out of this, and compare the performance with a more conventional slurry deposited electrode architecture based on tungsten oxide nanopowder. So that's the work of my student Thomas Cadden, and so he's carrying on with that work, and hopefully we'll see some more results from that in the near future as well. So that's a bit of a whistle-stop tour of my of the range of research that I've got ongoing here at Strathclyde, and I'd be happy to take any questions, and thanks very much for listening.
Thank you, Edward. It's a very broad portfolio of work you have done, and there are so many very promising projects ongoing, and I'm looking forward to your next talk about the results. So we have a question from Amruta. So thank you for nice presentation, Edward. So do you think flow batteries can play an important role for long-term storage, or are there some constraints and challenges to be considered?
Thanks. Well, I'd like to ask what you mean by long-term storage, but my sort of immediate answer would be yes. I think flow batteries are ideal, well, semi-ideal for long-term storage. depending on the chemistry. So there's bound to be some self-discharge of the electrolyte once it's charged up. And the question is, depending on the chemistry, how fast does that happen? And that will determine how long they can be used to store in between cycles. I think that's what the questioner means, but feel free to come back with clarification on that.
Okay, thank you. Don't see any, one from Ludmila. So in the Sub-Sahara one, do you have a local recycling strategy included in it?
That's a really nice question. We don't have that included in as part of the aims of this project.
So for the lead and lithium batteries.
Oh, so is that, do you mean sort of in the techno-economic modeling?
Yes, I mean just to have everything included. If you wanted to have a local system and grid installed, whether you consider have also local recycling strategies there.
Yeah, that is something that we're aware of, and we're taking it into account, but I don't know for certain whether that's sort of modeled explicitly in the Homer model, in the sort of cost estimations. I'll have to check that, but it is something that we've talked about, and not only the sort of end of life recycling, but also the maintenance and actually just the installation costs, because with lead and lithium ion, obviously there's probably not so much specialist sort of engineering skills needed to install, whereas with the flow battery, there's some material handling requirements that are a bit specialist. So that's something that we need to take into account.
Thank you. Maybe something to discuss in the workshop on sustainability of technology.
Yeah, I'd love to discuss that with you. Yeah.
Okay, thank you, Edward, again for the talk. From here, we welcome the last speaker of this session. It's Dr. Heather Wu from Imperial College London, and her talk will be on freestanding carbon hosts for lithium sulfur electrodes. So Heather is a Faraday Institution research fellow based at Imperial College London, working on cathode development for lithium sulfur batteries. So she holds an MSc in natural science from the University of Cambridge, and went on to gain a PhD from Imperial College, developing covalent modification strategies on carbon nanomaterials. She then did postdoc research positions at Queen Mary University of London and Imperial College, investigating the charge storage mechanism in hard carbon anodes for lithium, sodium ion batteries. So Heather, the floor is yours.
Sorry, I was just having trouble sharing the right screen. Am I sharing? No, I'm sharing the wrong one, aren't I?
You switch the display?
That's right. Okay. I think, am I sharing the correct screen now?
No. So you need to switch the display to full screen.
Has that switched it now?
No. You see on the
sorry, hang on, I'll just exit the presentation. Right, sorry about this. Okay, now am I sharing the right screen?
Yes.
Am I sharing the right screen now?
Yes.
Okay.
Yes.
All right. Perfect. Thank you. Sorry about that. Okay. So yeah, thank you very much for inviting me to the nice introduction, and also asking me to present. So I'll say a little bit about the work that we're doing in the group on making freestanding carbon hosts for lithium sulfur batteries. So again, I don't really need to give much introduction about why we need to be looking at alternatives to fossil fuels, but just two main two main areas that we will be shifting away from fossil fuels is to renewable grid energy storage and also to transportation. So as part of it, then batteries will be playing a key role in enabling this transition to net zero. So as I mentioned before, for grid energy storage, for sustainable renewable energy sources, and then for power for transportation. So I've just put some applications that, I mean, we use batteries for everything really these days, from very small handheld devices to then up to larger scale transport. But at the moment, it's lithium ion that's really dominating this market. But of course, we have to look beyond lithium ion batteries now, because for several reasons really, that the performance of current lithium ion batteries is reaching its limit with the current electrode materials that we have. And one thing that we should consider when we're looking for new battery technologies is that actually by increasing the capacity, we can increase and prolong the lifetime of the battery. And that, again, the better the performance, we can offset that against the environmental cost of manufacturing the battery. Another more obvious one is that actually in current lithium ion batteries, so the materials that we have in the cathode, and of course lithium itself is a bit of a problem, but in the cathode we have elements like cobalt, manganese and nickel, and they are considered critical elements, and they're only found in limited regions geographically. So the supply of those materials can cause bottlenecks in the production of lithium ion batteries. So what we need to be looking for is some sustainable alternative chemistries which can provide longer battery lifetimes that are based on more abundant materials. So in Magda's group, which is the group I'm working in, we've got some work on some different battery chemistries. So a lot of the work that we do in the group is based on sodium ion batteries, which is kind of the most obvious analog to lithium ion batteries. So you just replace the lithium technology with sodium. And we've got people also working on potassium ion batteries as well. And there's also redox flow batteries, which might be useful for larger scale grid storage, as mentioned in the previous talk. And then staying on lithium batteries, if we can replace one of the electrodes with lithium metal, it means we can actually massively increase the capacity of the battery. And so different options for that then are solid state batteries, so replacing the electrolyte with a solid state electrolyte, or replacing one of the electrodes with air, so in lithium air batteries, or as I'm going to talk about today, lithium sulfur batteries. So a lithium sulfur battery doesn't work in quite the same way as a traditional lithium ion battery. So at one electrode, on the anode side, you've got the lithium metal, and on the cathode side, you've got the sulfur. So the overall redox reaction that happens in the cell is that sulfur converts to lithium sulfide, and that typically happens at a voltage of around 2.15 volts. But it's not a straightforward conversion. It goes through the formation of a whole series of polysulfides, which I will discuss later on. So the advantages of this system is that sulfur has a really high theoretical capacity, and that means overall we can have quite a high theoretical specific energy in the cell. And so obviously this is a huge number that is probably not achievable, but the current best at the moment is about 500 watt hours per kilogram, and that compares to the lithium ion maximum really of 250. I think Tesla recently claimed 300 watt hours per kilogram. It's relatively lightweight, and then sulfur is cheap, abundant and non-toxic, and it's actually a byproduct of the petroleum refining industry. So in terms of applications then, so it's very lightweight, so it has a very good specific energy, but in terms of volumetric energy density, it's maybe not as competitive at the moment with lithium ion. So right now it's probably likely to enter the market where mass is the critical factor. So in larger vehicles such as space or automotive, so larger passenger vehicles. So the reduction of sulfur, as I mentioned earlier, it's not just a straightforward conversion between sulfur and lithium sulfide, but it goes through these series of intermediates that we call the polysulfides. And so these intermediates here are all soluble. So the conversion reaction actually takes place not in the cathode, but in the electrolyte solution. So there are several challenges that are associated then with this conversion reaction, in that when you convert from sulfur to lithium sulfide, you have a really large volume expansion. So we need an electrode system that can accommodate that volume change. Again, because we have the dissolution of these polysulfide species, it means that if they're dissolved in the electrolyte solution, they can shuttle, what we call shuttling, across the battery. And if they end up depositing elsewhere other than the cathode, it means that we've lost capacity from that shuttling effect, and that obviously affects the long-term cycling ability of the battery. And because again the reactions happen in the electrolyte, so it means actually you need quite a large amount of electrolyte in the solution, and it's not compatible with conventional organic carbonate electrolytes that are found in lithium-ion batteries. So alternative systems need to be found. Of course, again, one of the obvious ones is that sulfur is very non-conductive, so we need to add a conductive additive into the electrode. And then on the other side, with the lithium metal, you have the formation of lithium dendrites, which is obviously a huge safety concern. So the research really that I do is based on the cathode side, and it's really looking at the carbons that are used as the electrode support. So this is very common really in lots of the lithium sulfur research, is to employ carbon sulfur composites, and the carbon serves several roles really. So it is used as a conductive additive. It can provide a structural scaffold. So often one of the most common approaches is porous carbons that encapsulate the sulfur species and the polysulfide species, so physical encapsulation. But you can also have chemical trapping as well, where you have functionalized surfaces that can trap the sulfur and the polysulfide species to prevent any shuttling away from the cathode. And then there's also the potential to add catalytic elements into the carbon framework to try to increase the conversion of the polysulfides at the end. So one important thing to consider then, I mean, lots of research has been done in lithium sulfur batteries, and lots of quite effective carbon materials have been developed for lithium sulfur cathodes. But really, if we want to think about it actually being competitive with lithium-ion technology, or at least commercially relevant, we have to consider the overall energy density of the cells. So this graph on the right, we've got just the typical cell components. So if you think about the cell, we're not just considering the sulfur on its own, but you've got the different additives that you've got in the electrode. So you've got the carbon and the binder, you've got the foil, because normally we do a slurry coating onto an aluminium foil. And then we've got a huge mass from the electrolyte, and then we've got the lithium anode, and then we've got separator. So actually, if you consider that the cathode and the electrolyte contribute more than 75% of the cell weight. So if we want to increase the overall energy density, what we want is to increase the amount of the active material. So that's the sulfur loading inside the cell. And basically we want to then reduce the mass of everything else inside the cell. So that's the electrolyte and the current collector and the binder, if we can. So one good approach to doing that is to try to create freestanding electrodes. So if we can have a freestanding electrode, it means that we don't need the current collector and we don't need the binder. So this is an approach that we have been looking at so far in our group, is to use electrospun lignin-derived carbon fiber mats. So these have also been used previously in our group for work with supercapacitors. So this is just a schematic that I've taken from that. And the advantage is that lignin is again, it's a sustainable and cheap precursor, and it's a byproduct of the paper making industry. So in terms of a green process, it's quite a nice precursor to use. And then we can add different additives to the spinning solution to change the properties of the fibers. So the ones I've been making for now are use sodium thiosulfate as an additive. In just as a summary of what the spinning process is, we have a solution that is lignin dissolved with PEO in a NaOH solution, and then we electrospin the fibers. And then we can either do a stabilization step or skip that, and we can pyrolyze it at different temperatures under nitrogen. And then once it's washed, we end up with these porous carbon fiber mats. So this is what the fibers look like. So they're several microns in diameter. And from the Raman spectrum, you can see that they've got typical hard carbon structure after pyrolysis at 1000 degrees. But again, if you increase the carbonization temperature, you can increase the graphitization. But then the mat becomes more brittle and quite difficult to handle. And then we can see here from the XPS that actually we have quite a high oxygen content in these fibers and some degree of nitrogen and sulfur doping. And so we think that these might be quite beneficial for interactions with the polysulfides during battery operation. So then in terms of the porosity, it's got quite a high surface area of around 850 meters squared per gram. And then we've got a mix of micropores and mesopores. So looking at the pore volume then, we can see that if we calculate a theoretical sulfur loading, that actually in terms of what we can put into the micropores and the mesopores, we can accommodate, if it's just in the pores, around 54 weight% of sulfur. So it's possible to accommodate quite a large amount of sulfur purely within the pores and not even on the surface of the fibers. So then I assembled these carbon fiber mats into some batteries. And typically with these with lithium sulfur batteries, people start with elemental sulfur, but with these fibers, it's actually a lot easier to start not with sulfur as starting material, but already with the lithium polysulfide. So here I started with Li2S8. The advantage of that is you can drop cast it onto the mat, and it's very, if you know the concentration, you know the volume, then it's very easy to control your sulfur loading. So then we do a first discharge, and that gives us that has a theoretical capacity of 1460 milliamp hours per gram roughly, and then you charge it fully and you go back to sulfur. So you in theory should obtain the full capacity from that. So from the CV we can see that we've got the typical reduction and oxidation steps here that go quite nicely, and then impedance before and after cycling, we can see that the impedance before cycling, the charge transfer resistance decreases after 5 cycles, and that suggests that with the cycling we are improving the wetting of our electrode, which again is a good thing in terms of the interaction of the carbon with the electrolyte and the polysulfides in solution. So then when we look at the galvanostatic cycling, we can see that we managed to achieve a very high initial capacity of around 1,200 milliamp hours per gram, and that's equivalent to 71% sulfur utilization. So we're not accessing fully all of the sulfur, sorry, but this is still reasonably high for this material, and it remains quite stable over 50 cycles. But obviously this is quite preliminary work at the moment, so there's still lots of optimization to be done for this system. So the commercially relevant targets, typically we're aiming for a much lower electrolyte to sulfur ratio. At the moment I'm using 10.4, but the target really is less than 5 microliters per milligram. And as I said before, we want to increase the sulfur loading. So here I've loaded it with about 56 weight% to match the pore volume, and that is equivalent to an aerial sulfur loading of 4.8 milligrams per centimeter squared, but the target is to reach over 5. And then again here my carbon to sulfur loading is quite high, and the aim is to reduce it to below 5%, but that is quite an extreme target. So there's still some work to be done there. So just as a quick comparison then, I just wanted to quickly show there's a commercial sulfur cathode available that is 70 weight% sulfur loading, but this is a slurry coating on aluminium foil. So I just wanted to compare that actually here we can lose some mass by not having to have the aluminium current collector. Although our carbon, the aerial carbon loading is higher than the amount of carbon black and the binder that they put in, overall our total inactive component mass is lower, and we've managed to achieve a higher sulfur loading. And then in terms of the experimental capacity, the NEI website states that their cathode can achieve 800 milliamp hours per gram, but in this case, we've achieved around 1200. And so if we only consider the cathode components within the cell, then actually we can increase the energy density by around 70%, which is not bad at all for some initial results. So yeah, so as I said, this is still ongoing work, but hopefully I've shown you that lithium sulfur is a promising new battery technology, but obviously there's lots of challenges still to address. So we've got the challenges of polysulfide shuttling, we've got to accommodate the large volume expansion and to control the lithium sulfide precipitation. But at the same time, we also need to consider the energy density of the cells. So freestanding electrodes are a good approach to that. And yes, so it's still early days with this work, but hopefully we can optimize the cell to make it commercially relevant. So I'd just like to thank the group. So actually the fibers are not my work really at all. They were spun by Julian and some of them were spun by Savan. I'd like to thank Maria as well for her help, and also to thank Magda. And this work, I should just say, is part of the Faraday Institution project. So yeah, I'd like to thank the TTUT group too, and I'd like to thank you for your attention.
Thank you, Heather, for the very nice talk. So I don't see question.
I would have maybe one.
Yeah, you can go ahead. Yeah.
I would as well. Yeah. I'm just I picked up on one of your slides where you said sulfur is a byproduct of the petroleum refining industry. So what is your view for the future of these batteries? So if they will make it, where would your sulfur come from? Are there other sources, for example?
No, it's quite interesting that I was thinking about it the other day. That yeah, it's true that we want to replace the petroleum industry, the oil and petroleum industry, but actually we're obtaining sulfur as a byproduct from it. But I think, I mean, in terms of the sulfur reserves that are already there, there's a huge amount of sulfur. I think. I mean, I don't know about the LCA of the life cycle assessment of all the techno-economic analysis of this, but I think it would still be economically viable in the sense that we cannot phase out, as in the phasing out of oil and gas is not going to be immediate. So I think during that transition period, it will still be viable to obtain sulfur. And then from that point on, there will be, again, hopefully there'll be better recovery and recycling methods as well. But I don't know very much about that, I'm afraid.
Yeah, we're certainly not short on sulfur. It's one of the most abundant elements. It's probably a good idea. Thank you. It was a really wonderful talk. I really enjoyed it.
Yeah, I think it's kind of also answered Amruta's question, which also about the byproduct and also the impact on the emission saving and life cycle assessment. But I guess we could talk about it in more detail in the workshop. There's one from E. So two questions actually. So did the carbon fiber have capacity during the charge discharge process? And the second question is, at the last slide, the CV plot has two pair of redox peaks, and it's different with the CV you mentioned before. What is the difference between these two CV?
Okay, that's a good question. I kind of glossed over that, to be honest. So there is some capacity from the fiber, but this is something I'm still trying to understand, because there's a certain degree, I would describe it as protection of the fiber by the sulfur deposits. So if you just test the fiber itself, because it has such a large surface area, I think you have a lot of what's called, like the degradation of certain electrolyte species on the fiber. But I think when you're cycling it with well, first of all, I think those happen at a much lower voltage. So we're cycling between 2.8 and 1.8, and I think those degradation reactions happen below around 1.5 volts. And then I think there's also the element that you're kind of coating the fiber with this protecting layer of sulfur. And again, because we're charging at a relatively high current density relative to the carbon capacity rather than relative to the sulfur, we don't really see that much effect from the carbon. And for the CV, yes, so this is a question that I need to answer too. So in other materials that we have made, like the traditional porous carbons that they use for sulfur encapsulation, we see these two redox peaks. And in the CV that I showed for the fibers, you only really see that one peak. And I'm not entirely sure why we don't see the second peak, because the galvanostatic charge discharge shows two plateau regions that suggest we have two processes happening. So I've yet to kind of reconcile the differences between those two, but I am considering it right now.
Okay, thank you. I think in the interest of time, we should move on to the workshop. So I think Edward has a question on the cost effectiveness, but I guess we could also discuss that during the workshop. So Ludmila, you want to introduce the workshop a bit?
Yes, I'm just trying to share my screen. Here you go. So yeah, in the workshop, we aim a bit of a conversation on a larger scale, a bit about yourself, so that it's a networking event, as we wrote also on the flyer, but also to have the sustainability in mind when talking about energy storage technologies, and whether you always see it yourself in your research, and whether you see it translated, in industry already, or when governments actually discuss. So maybe this is a set of questions that will be addressed under this topic. And then the last two are more about the ECR community, that we want to engage much more in the topic, and also in research on net zero in general, linked to energy storage, and where you see opportunities to have your voice heard, and also kind of to engage in, for example, the supergen as an ECR yourselves. So I think with this, we could already go into the breakout rooms, and there will be facilitators that will lead the discussion a little bit around these four topics, and have more precise questions, I think, that we can then summarize. And we hope to then get a document out with your summaries, especially also now that this workshop is much shorter than we actually anticipated. We might have the summary of the breakout rooms a little bit shorter today, but maybe hope to have a decent article published on the Supergen website, or maybe even a communication in a scientific scope about this workshop and about your ideas. So please be active and engage. Right. I hope you enjoyed the workshop. Many left. I think we need to assure people that it's not that difficult to discuss, and it's more of an opinion thing and less about knowing facts to engage in the discussions. So we would like to hear back from you if you wanted to get involved, or in the last point of discussion, I'm not sure if you had time to discuss this. So how the ECR network can be more more visible, let's say, in the country on different levels, from going from public to industry to policymakers and government. And the event that Yongyang was highlighting in September, maybe you could, if you wanted, you could also join and see what is discussed there, because I think this will be on the level higher than ECR. I'm not sure of your time, but we actually planned to hear back from every breakout room before we end the session. But I might just ask Amruta, Lola, and Binjan whether you took notes. I took some notes from our meeting. I think we also did. So maybe we could shorten it here and discuss amongst us then afterwards.
Yeah, so actually we also took some notes, and Ola was actually going to give us brief in our group, but as you mentioned, if time is the limit, then Ola, is it okay that we already have some inputs from our group written down? So okay.
I'm open. I could stay 5 more minutes to have a conclusion if the participants are keen to stay on as well. I'm happy to give a feedback from the breakout rooms.
Okay, so we spoke about some of the questions, and we spoke about the energy storage technologies contributing to efforts related to climate change. And we just felt that rather than one technology, it was like a portfolio or a mix of technologies that could actually deliver the change we're interested in. And we spoke about, different kind of renewable energy technologies, contributing to things like CO2 reduction, and also considering things related to seasonal variability to deliver some of these solutions. We also spoke about different parameters we needed to achieve sustainability, and we spoke about life cycle assessment. And one of the key things that we also spoke about was the fact that most people, why they actually don't consider sustainability in research is because first, the way the project has been written, it's more focused on performance optimization rather than considering things like sustainable materials, critical materials. And one thing that was also highlighted was the need for maybe like a workshop on LCA, because people don't really understand what should be done to answer some of all these key questions. Then we also concluded by highlighting how the energy network could actually improve communications with ECRs. So some of the suggestions were, just a minute, please, was like some researchers would like to see, maybe like industrial partner requirements and places where, other early career researchers can talk about what they're working on and their capabilities. And they're also interested in workshops on different topics like tutorial style. That's it from us.
Thank you, Lola. Vijayan, do you want to also summarize a bit?
Yeah, so I think we have a habit talk inside our room, small room. So it is we compare different kinds of energy storage, from battery to larger scale, such as liquid energy storage. So we think different storage methods should have different application scenario. And also we discussed about how to expand our voice among or beyond the community. So I would just suggest maybe they are making a video to show their lab work. I think it's a good method. And also Rashma proposed maybe and Alex proposed maybe we use some research demo or something to make our voice to be heard. And also most of us agree to, we need to add a post session maybe for next workshop, because currently our workshop the time is limited. So maybe if we have a post session, we let more people know our research, to read our research. Yeah, and also maybe we can raise some post or oral prize next time to try for more people to attend us. Yeah, so that's all from us.
Mm-hmm. Yeah, I also just maybe summarize and Hui interrupt me or add later for what I have forgotten maybe. So I think we discussed about sustainability of the grid and of energy storage in general. We discussed a little bit centralized and decentralized storage, and you just mentioned Lola, that the project outline and also that the project that I think Edward discussed, this is the key of where to think about sustainability and thinking about whether in developing countries it's better to have a large national grid or to have smaller grids still, but a little bit more decentralized, that may be cheaper to run and have less failures and easier to operate. But in general, too small things, too decentralized might lead to higher cost, and also more is kind of more difficult to model as well, because it doesn't have as much buffer, I guess. Then we talked about that there are companies that have these shutdown mechanisms now, so to really buffer the grid. So it's maybe not the most sustainable way, but it can take off some peak demand. And on the sustainability, I think Corentin mentioned what I found really a good thought is that by 2040, 2050, that's where we're looking at to be really net zero. But then probably the whole system needs an overhaul, and batteries need to be replaced and recycled. So we need to be prepared for that and take this also into account. And on the ECR engagement, we had Duncan actually also on our group, and he hasn't been in research for the past few years. And so we discussed a little bit how to be visible to companies, governments, and also the public as ECRs and kind of research in general. And so, for example, newsletters, I think, were something that Duncan, for example, was interested in, but social media is a very controversial point. So only using social media might be dangerous, because we will be talking to kind of a very small group of people that has only similar interests and not really to the wider audience. So we might be separating ourselves out. And also how to engage the public is probably a very difficult question, and how much we have to educate the public and also industries and policymakers, and how ECRs could engage more in that. I think there are lots of ideas to be developed, because I think there's no real clear vision for that. We mentioned the science museum, so somewhere where the public is going to might be a way to really make not only our research visible, but also our vision towards net zero as well. Yeah, I think that's kind of my summary.
Just a quick update, Ludmila. So what we thought in our group, whatever questionnaire which we prepared for the workshop, because there was less time, so we will send this questionnaire to all our attendees, and like we will try to follow up with that with them, so that if there is something interesting coming up through that, we can publish it, as you mentioned, on the Supergens website, or then it can be further followed through for some proposal writing or something, if some good ideas come through there.
Mm-hmm. Great. Okay, so with that, I think we could conclude this this event. I hope you enjoyed it, and I think we had quite good numbers to begin with, let's say. Hopefully we can increase those next time. And yeah, as was suggested, I think poster sessions might be a very good idea to engage more people in the workshop.